Yeah, so let's start today's class. We'll take on a new logic style which is known as pass transistor logic. Right? Okay, this we discussed in the very first class. We can use NMOS as an switch, but NMOS is an can transmit a perfect 0, but it cannot transmit an perfect 1. So if you recollect, suppose this is VDD out here and you want to switch it on this NMOS. So on the gate we give an VDD, right? So this has to switch on, but the output, if you see here, as it keeps increasing, the moment it reaches VDD minus VTN, this NMOS gets switched off, because if it has reached VDD minus VTN, the gate to source voltage now will be, it is VDD out here and it is in a VDD minus VTN. So the gate to source voltage is just VTN. So if it goes beyond that, then the voltage available here will be less than VTN, and hence this cannot go beyond that. It will get switched off, right? Now why do we call, if you remember, why do we call this as drain and this as source, and not call this as source and assume that okay, this will be switched on? Because this is an NMOS out here. So the electrons, the positive charges will flow from drain to source, and the negative, the electrons will flow from the source to drain. Since the flow of the electrons is from here to here, from right to left, so we call this right terminal as source here in this particular configuration, right? Okay, but when we have to transmit an 0, right, we give a 0 here, and we suppose this is VDD initially, right? Now if you see here, this becomes the source. Why? Because again, see, the positive charges is going to flow from the drain to source, and the source is the electrons is going to flow in the opposite direction. So this becomes the source, and in this case, since it is 0 here and it is VDD here, irrespective of what voltage is available here, this gate to source voltage is VDD, which is higher than VDD, VTN, right? So this entire voltage which is available here will get discharged to 0. So that is what NMOS passes a perfect 0 but not 1. Right? And same is the case for PMOS. It's just the opposite, where PMOS can pass a perfect 1 but not 0. So if you have an PMOS here, now to switch on an PMOS, we know we need to apply 0 and not VDD. So when we apply a VDD here, so this will become the source, because the positive charges are going to flow like this, because this is PMOS and the dominant charges are in a PMOS are holes. So that's why this becomes the source here. Now if you see here, irrespective of the voltage out here, VSG is VDD, okay, which is greater than the threshold voltage, and hence this continues to charge this output voltage till it reaches an VDD. So this can pass an 1 without any issues. The entire voltage will be available. Whereas if the PMOS has to transmit an 0, it has a similar problem as that of NMOS while transmitting 1. Right? Now if you see here, now this is VDD initially, and this is 0. Now it is trying to discharge this to 0, but the moment this voltage, and now this becomes the source, because the positive charges are moving from here to here, right, from the left to right. So the moment this reaches an VTP, right, then this voltage, and this is 0 here, so this PMOS gets switched off. So hence we will find that this is not an good transmitter of 0. Okay, so that is what. Like now using these properties of the NMOS and PMOS, so we'll initially just consider pass transistor gates just with NMOS and see how we can realize the various functions. Okay, now suppose I have to have a function and just AB. Okay, so if I have just A and B out here, will this function work properly? If you see here, this is A, right? So if I give A 0, right, and so irrespective of whether B is 0 or 1, the output out will be 0 here, and if A is 1 and B is also 1, this output will be 1. So is only this much sufficient? It's not sufficient, right? Because see, whenever B is 0, okay, this will become a floating node, right? So you can't have a floating node, right? So that is the reason. That is the reason for all the 4 possible combinations of input and output, there has to be either VDD connected here or ground out here. You can't have a floating node, right? So that is why you require 2 transistors here. Now if you see here, if B is 1, then this output will be connected to A. So if A is equal to 0, it will be 0. If A is equal to 1, it will be 1. And when B is equal to 0, you will find that this 0 will come here. So for all the 4 combinations, the output is either connected to VDD or ground. It is not left floating. Okay, so that is important out here, right? It is not left floating. Either it has a connection to 0 or through or to A. Okay, both are NMOS. Both has to be NMOS, right? See, if B is equal to 1, this NMOS will be switched on. So you will have A coming here. If B is equal to 1, right, B is equal to 0, then this path will be activated. This is also an NMOS. So that this 0 will be available here. We can't have right, and a situation where F is floating. Okay. Similarly for an OR gate. Okay, if you see here, if B is 1, right, if B is 1, then it's OR, right? So this 1 will come here, and if B is 0, okay, again both are NMOS in this case also. If B is 0, then A will come here. Now A can have either 0 or value 1. So obviously if it is 1, it will be 1 here, 0 will be. So again you will find that this is not this is an pass transistor OR logic. This is known as an pass transistor OR logic. This is known as an pass transistor AND logic. Okay. Okay. So that is what. Now when we are using the pass transistor logic, and then probably this is only NMOS PTL we are using. Okay, you can have a similar thing for PMOS logic. Only PMOS also you can use it. So suppose I am using an when F is equal to AP, output will not get full VDD. Yeah, that's what I'm showing here exactly. That is what I'm showing here. See, whenever we use an NMOS as an switch out here, so you will find this X is what is shown out here, right? So for 0 it will be 0. For 1 it will be not full VDD. Okay, so to restore the final level, you might have to after several pass transistor logics are being implemented, in the final stage you might want to have an inverter to restore back the levels to VDD, right? If you see here, right? So unless you have an inverter, also inverter is a simple static circuit. Simple static inverter, right? So to restore the levels finally after the pass transistor logics, we might have to use one inverter. Okay, so then it will get restored, because you see here when we are using pass transistor, it won't be rail to rail voltage. For specifically if I speak about we'll see that it depends on the functions, right? You can use 2 inverters. You don't have to make a domino logic and all, because when we are talking about domino logic and all, then we are moving into dynamic law where there is a clock and all. So here, if you don't want an inverting output, then you can use 2 set of inverters, or you can implement the invert function here itself, right? Instead of and you can with a pass transistor you can implement an AND also. Suppose I want an AND function here, so instead of implementing an AND function, I can implement a NAND also. So I'll give that logic very soon in next few slides. So you'll understand that not necessarily here the point at X, you can implement a positive function or a negative function. It is very easy. Okay, the logic is very simple in implementing any function out here. Both positive and negative functions can be implemented, and then you can use an inverter to this. Okay, so when we are using an inverter, we need to be a bit careful with the threshold voltages. Okay, suppose this is 2.5 volt, this is 2.5 volt, right? Now this will be charged to what? 2.5 minus threshold voltage, right? And here also you will have 2.5 minus threshold voltage, right? So suppose the threshold voltage of PMOS and the NMOS are the same, okay, then this will be just in the edge of cutoff, right? Okay, because suppose this is let's assume a case where a threshold voltage is 1 volt. Okay, let's make it more specific. So this will be charged to 1.5 volt, right? So if threshold, then it will be 2.5 here and 1.5 here, right? And so this will be just in the edge of the switching on, right? Now if you see here, there is an this transistor suffers from body bias condition, right? Because the source is not grounded out here, so the threshold voltage will be higher. Okay, if the threshold voltage is higher, then this will be charged to not charged to even 1.5 volt, it will be charged to below 1.5 volt, and if it is charged to below 1.5 volt, this M2 will be on. So you have an issue of a short circuit current here. Both these transistors will be switched on in that case. Okay, is it understood, or should I repeat it once more? Right? Okay. Okay, good. So see, this is 2.5 volt, this is 2.5 volt. Okay, let's assume that the threshold voltage of the NMOS and the PMOS is 1 volt. Okay, if it is 1 volt, right, I am going to transmit one out here, right? So instead of full 2.5 volt here, I am going to get 1.5 volt here. So if I get 1.5 volt here, obviously I am transmitting a 1 here, so this M1 will be switched on. Correct? Since I am transmitting 1, this has to be switched on. This will be switched on. What about M2? It is 1.5 volt here and 2.5 volt here. So this will be in just VTN. So this will be just at the edge of being switched on. Okay, still I can consider, okay, it has to be, it is just VTN, I can consider, okay, it might be switched off. Okay, you can take that. But the problem is more serious here, because this transistor suffers from body bias. Okay, what is body bias? If the source is not if the body is not if the source is higher potential than the ground, then the VTN increases, right? So this transistor has got a body bias problem issue. So because of which the voltage across the VTN increases. So instead of 1 volt, it could be 1.2 volt, right? It can increase. If it is 1.2 volt here, then this voltage will not be 1.5, and instead it can be much lesser than 1.5 volt, right? In that case, the body to the gate to source voltage here will exceed the threshold voltage, so this will also be switched on. Is it understood now, Sridhar? Yeah, okay. So this NMOS only PTL, this suffers from this particular issue. So we need to take care of that. So how to take care of that? There are several solutions available out here. One is like we did it in the domino. Suppose this is 1, it will be 0 here. Okay, if it is 0, you can switch on this transistor. Okay, this is known as an level restore. So this PMOS will charge it to VDD. If it is charged to VDD, this PMOS will get switched off. Okay, and this will be switched on. So there will be no issue. Okay, so whenever this is 1, this will be 0, and if this is 0, this will be switched. Can you foresee the issues in this? Anybody? from whatever we have learned till now, will there be some issue out here? Anybody can make an guess? Okay. Let me tell you, suppose initially this was 1 out here, now this becomes 1 out here. Okay, static condition, this is 1, this is 1 out here, and this has been restored to 1. Now when this is going to 0, right, when this is going to 0, this voltage is dropped, so this will try to discharge this node to 0, whereas this is trying to charge this node, keep at this voltage at VDD, right? So this has to be much stronger. So this has to overcome the current of this transistor to pull this to 0, right? So that means there is a ratio issue out here, right? You need to, this becomes a kind of a ratioed logic. Unless you give an high voltage out, unless this transistor is able to draw large currents, then only that, once this starts, but once this switching happens, this becomes 0 out here, this will become 1 and this will get switched on. But that initial force which is required, okay, that has to be catered by keeping this size larger. Okay, so how the transistor sizes are calculated? In past transistors, okay, if you have a larger size, okay, then the delay will be lesser. Okay, so we'll see how to calculate the delays. Okay, that's all. It is not an ratio, like you don't have a PMOS, NMOS, things like that. In this particular circuit, obviously the NMOS has to be kept in a much stronger than the PMOS. Okay, so that through simulation also we can fix the value. I'll show you one graph which will show the effects. Now if you see here, now here this is the level restorer width of here, right? If you keep the W by L strong, then it will take that much more time for the output to go to low. Now here it is not even going to low because you have kept the W by you have kept that that PMOS very strong here. So you keep decreasing the width of that PMOS. Here it is, the output is finally going to low. Here it is going pretty fast. So if you keep this very strong, then there could be a situation where this output may not go to low at all. So you have to keep this weak PMOS, right? Generally we try to keep it weak by increasing the length of the transistor and using minimum width. Okay, so that needs to be done. So that's how you have to take care whenever you are using the level restorer. This some of you had encountered this problem during your dynamic logic implementation also. So this transistor has to be kept in a weak. Okay, it cannot be a strong transistor. It's the only purpose is to just to restore the level. Okay, so yeah, when I say W by L, it means strong means W by L is larger. Okay. How large size contributes to lesser delay for PTL? Because see, you can model this as a resistance and a capacitance, right? So the value of the resistance decreases with increased W. Okay, is it okay? I will see that in one of the slides. Okay, right? Okay, this we learned about this, right? Okay, then this was one solution. Okay, this was one solution. Now we are discussing a second solution. In the second solution, it says, okay, you go to low VT, or there are devices whose VT is almost 0. Okay, if you have an almost VT 0, the problem here will be, suppose now there is an inverter here, there is an inverter here, and you are using a pass transistor to club the outputs out here, right? So now if you see here, this is switched on and this is switched off. So this voltage, high voltage, can come from here, and if the VT of this transistor is very low, you could have a current flowing like this. right? So the leakage current is likely to increase. So that is a normal thing which can happen anywhere, right? If you if you use pass transistors gate with low VT, right? So then if you use low VT, this voltage will become close to VDD, right? Right, that's what, right? This voltage, the problem here was the voltage available here is VDD minus VTN. Now if you reduce VTN, this will get close to VDD, so that resolves the problem. But low VTN always causes a leakage current. So when you have inputs coming from other circuits, so low VTN will increase in static leakage. So you got to be careful with using low VTs also. So every circuit has got its own advantages and disadvantages. You should be aware what is the pros and cons of each design. That's all. Okay. Now let us just try and understand what happens in these particular configurations. Okay. I have 4 volt here. I have 5 volt here. They are all NMOS. Okay. VDD is 5 volt. VT is 1 volt. What is the expected voltage here? Can anybody tell me what will be the expected voltage out here? Yeah, it will be 4 volt. What about here? The second case? Yeah, second case also it will be. And what about the third case? Yeah, 3 volt. Yeah, exactly. So it will be 4 volt here, 4 volt here, 4 volt here. It will be 1 volt is the here. 1 volt gets dropped as VT here. Here also 1 volt from here VGS minus VT. So 1 volt has to get dropped here. Here also 1 volt can has to get dropped here, but the total available voltage here is just 3 volt. Yeah, VGS minus VT or input, whichever is smaller. Exactly. So that is the one. So here if you see, there are a few more conditions given here. What about here? The first case? Yeah, 2 volt. Second case? 2. And what about the third one? Yeah. In the third one, it will be 3 volt. Okay. Because it is 4 volt, 1 volt, 5 volt is available here, right? Okay. So this is what and how an NMOS switches work, right? Now you have an series of NMOS which are connected here, right? That general mistake what we make is we think that at every stage, okay, there will be an VTN drop. Okay, that doesn't happen. Okay, now it is VDD here, it is VDD here. So here it will be VDD VTN1, right, minus VTN1. Here again it will be VDD minus VTN2. Okay, if you assume that if you just neglect the body bias, okay, of each of these transistors, the final output will be VDD minus VTN. So when you are moving across in an PTN in a pass transistor logic chain, okay, it is not that at every stage VTN will be lost. Okay, only one VTN will be lost. Is this understood by all of you? Right? Yeah. Okay. So in a PTA when a pass transistor logic, okay, don't think that every stage there will be one VTN loss. Okay, when we generally make a PTN circuits, okay, long chain also, only one VTN loss will be there. Okay, so that is about NMOS PTN. Okay, then for many circuits, when we implement an yeah, we are assuming that VTN is symmetrical. Actually, the body bias effect for each nodes will be slightly different, and hence there will be a minor change in VTN of all the transistors. Okay, so you might have we studied about body bias, right? So that is the reason. Okay, like when we make complementary circuits, okay, we generally implement both F and F bar, because in the next stage you might have to use F and F bar also, right? It is better that you generally have on both the output. So if that be the case, so we can implement it like this, right? Now if you see here, this is an A B, like A is equal to 1, B is equal to 1, it will be 1 here, and if B is equal to here, right, if B is equal to 0, then it will be 0 straight away out here. So you will find, and if B is equal to 1 and A is equal to 0, then also. So this is A and B, right? And now to implement an NAND also, it is very simple out here. If you see here, this is an A bar here, right? So if you have B is equal to 1 and A is equal to 0, right, then you will have an 1 out here, right? And similarly, if A is equal to 1 and B is equal to 1, you will have a 0 out here. So the NAND will get implemented here, right? So you will find here, so all the functions are implementable easy. Now how to think of designing, what is the step which is involved in designing all these things? Okay, first I take, like, it is AB, right? If F is equal to AB, if I have to implement, first of all I put two transistors. I'll put B here, I'll put B bar here, right? Both are NMOS. I put B here, B bar here. Now in the function, here I am putting B, so I put B equal to 1. So what is the function? F transforms to A, so I put A here. Now again, for the B bar connection, I put B bar, right? So I put B is equal to 0. What is F? In this case, if I put an B bar, I think it becomes an 0, right? Right? So I can put a 0 also here. Okay, still it would work. It will work, right? If I put a 0 also, it will work fine here. If I put B also, it will work, or I can put a 0 also, because B bar is as a 0, so I can put a 0 here also. I can put a 0 here. Same thing for any gate function, right? If you have to implement, you can do that. And how to make the principle of design is like this. You take one of the thing as an variable, put two gates for 0 and 1, and put that value in the function. So whatever you get, you just keep putting here, right? So it has been put B here, but 0 also would work fine. Similarly, if you say let A or B, if you say here B is equal to 0, if I put B is equal to 0, what? A remains, right? So B is equal to 0, I put A, right? And B is equal to 1, if I put B is equal to 1, F remains 1 actually, right? So I can put 1 here. So even if I put B also, because I am talking about B equal to 1 condition, so we have put B here, but I can put 1 also. Okay, since it is for this particular function, I can put 1. It is known small function, but when I am designing a large function, I can just put 1 also there. Okay, so this is how I design a PTL logic. Okay. Now you can see what we can do is, the third solution is use a transmission gate. Okay, what is a transmission gate is, instead of using just NMOS, I am going to here. Okay, so I am telling you that the logic for implementing an NAND gate, complement here, NAND gate, right? This is NAND gate, right? Okay, now for a NAND gate, if I have to implement an NAND gate, if I put an A is equal to, now this is B, right? So this is B. If I put B equal to 1, what would remain? A bar. So I put A bar here, correct? And if I put B equal to 0, B equal to 1 here, okay, B equal to 1 here, it remains an A bar. If I put B equal to 0 here, then this becomes 0. So I can put a 0 also here. Is it okay, Rajesh? Yeah, you can do that. Okay, I'll give you one more example of a full adder. How to implement, how to design that. These things will become absolutely clear then. Okay, so I can use a transmission gate also. Okay, this is the third solution. What is a transmission gate? Transmission gate is, okay, see, you instead of using just an NMOS, you use an PMOS also in parallel. So if you use an PMOS in parallel, what happens is, the NMOS will transmit a good 0 and PMOS will transmit a good 1. Okay, so they will work in conjunction. So the output voltage available here will be rail to rail. Okay, only thing is the control signals will be complementary, right? Now suppose I want this switch to be switched on for C equal to 1. So for in the PMOS I need to give C bar. Okay, I need to give C bar. The current direction could be either way, right? If it is, if already this node is charged to 1 in the previous stage, then if I give it a 0, this will be discharged. Okay, and if I have this already 0, and if it is 1, the current will be going towards that side. Okay, so that is the, so you can have both ways, right? Currents flowing in both the ways, right? Is it okay? Okay, yeah, yeah. Is there some issue out here? Is it okay with all of you? It's okay. Okay, right? Okay, although I have shown here A, B and here, right? When we design, we can put zeros and ones also here, right? Okay, so don't worry about that. We can do that also. Okay, now if you see the resistance of the transmission gate, right? Right, if you see here, suppose I have to transmit an 1 out here, right? I said the NMOS transistor, as the output reaches high, the NMOS transistor will be switched off, and the resistance of the NMOS will go up. The NMOS will get switched off, right? So the NMOS resistance will go to infinite, right? Whereas PMOS, it will be initially it will be in saturation, then it will slowly come into a linear region. So this is what the red line which shows is the PMOS resistance, and the parallel resistance will be something like this for an where the graphs will be slightly different when we are transmitting, and this is when we are transmitting a 1. When we are transmitting a 0, the PMOS resistance will go to infinity, and NMOS will remain like this, and then the resultant there also will be something like which is shown in the green. Is this graph understood by all of you? Right, initially the output is 0 here, right? This is 2.5, so the NMOS is switched on. Okay, it is in saturation region, so least resistance, right? But as the output keeps increasing, the NMOS will get switched off, so thus NMOS resistance will go to infinite. Whereas PMOS, it will continue to remain in the, initially it will be in saturation region, but later on it will come into linear region because VDS drops, right? But it will not get cut off. So hence that PMOS resistance, okay, it is going to remain like this. So the net resistance is going to come like this. Okay, so that is the reason we use a combination of NMOS and PMOS, right? So this is an multiplexer. Okay, so these days most of the multiplexers are made using pass transistors. Okay, so you have, see, this is the select line. So whenever the select line is high, A will be selected here, right? And if the select line is low, right, and so B will be selected here, right? So you see here, select line is high, so this PMOS will be switched off, switched on whenever select line is high, and this NMOS will be switched on. So these both will parallelly get switched on, and when the select line is low, okay, so you have this NMOS being switched on and this PMOS also being so B will be diverted out here, right? So you need not have a pass transistor also here. Since you already have a level register, you could have just an NMOS switch A, B, right? So if you, this is just showing an multiplexer where you have just a 2 into 1. Even if you have an 8 into 1, 10 into 1, or whatever, 16 into 1, all those things are these days implemented using a pass transistor. So earlier days you had all those AND gates, and one of the AND gates will be selected. Here here we are, it saves lot of power as well as area while using pass transistor. Okay. Okay, let me repeat it once again. This is a multiplexer. Okay, multiplexer is like if select line is 0 out here, suppose select line is 0 out here. So this PMOS will be switched on, and since S bar is given to this NMOS, B will be routed to this line, right? Okay, and similarly, if the select line is 1, right, then this NMOS and this PMOS will be switched on, and A will be selected here, right? So this is a multiplexer, right? Depending on S, either A will be routed here or B will be routed here. Is it okay, Doshi? One of the inputs, yeah, okay. Now I am telling here that this is just only 2 switches are used here. You can have 4 switches, and you can have S1, S2 also, right? This is used to to restore the level, but in this case it is not required because you are using a complementary circuit. Even otherwise, okay, this is also used so that the outputs of the multiplexers, okay, this acts like a driver circuit also, because this is going to drive the next circuit. Okay, so this can cater for the fan out requirements, right? So you can all the multiplexers these days are implemented using pass transistor logics. Okay, I have just shown just a 2-into-1 multiplexer. Okay, even higher multiplexers are also higher multiplexers is what you could have an n number of inputs, and out of which only one will be selected, right? So you can have a set of so you will have a decoder. Where to select one of the, so the decoder, one of the will select one using a decoder. You can select one of the pass transistors to be switched on, right? So that is how you understand what a decoder is, right? So you have 3 select lines, you can have 8 input lines, and that those 3 select lines you give it to a decoder and get one output. One of the outputs will be triggered on. So you can use a decoder and make a multiplexer. Okay, DMUX, decoder, right? To generate the control signals, right? So this I am using only S. Suppose I have 4 transistors, right? And I have signal S0 and S1. So one of them needs to be. So I use a decoder there. Yeah, it is wired OR. Yeah, for all multiplexers it will be wired OR, right? Okay. So now we talk about the delay in the gate. Okay, what is the delay in the gate? Now if you see here, these are transistors. So all these pass transistors can be called as an R equivalent, right? This we saw, right? What is the value or how to calculate? So you can model it in this way also, right? Or you can, what you can have is in betweens you can have certain buffers in between. Okay, so either you can have a chain of just pass transistors, or you could have buffers. Okay, once if it is just a chain of RC, then if you assume that all R equivalents and all these are same and all the values of RC, right? So that we did this buffer means it is a, you can call it as an 2 inverters cascaded one after the other. Okay, so you can do that. Okay. So okay, I was telling, see, this we saw, right? 0.69 into C equivalent when we studied about the number of RC delay, inverter delay, right? So K means if the number of stages here, K, right? So if there are K transistors, so the delay will be 0.69 C R equivalent, right? And R equivalent, and K 0 to K can be from 0 to N, right? So so this turns out to be N into N plus 1 by 2, right? So this is what the total delay. It would be the total delay. In case there is a buffer in between, there are going to be buffers, then the equation gets modified. Okay, so if there are, after every m, if there is a buffer, then this gets m into n plus 1 by 2 plus there will be these many buffers in between. So n divided by m minus 1, these many buffers. So this gets this equation gets modified like this. Okay. So what is the now if you differentiate this particular equation considering m as an variable, what is m? After how m is the number of stages you used, and then you use a buffer, right? So any specific use of buffer? No. See, when you use a buffer, the delays will reduce, because if you see here, the voltages available here is decreasing by VTH, right? So you will find that now if you use a buffer out here, so it will be restored back those voltages. So if you see here in this equation, so you will find that because of the buffer, the delay will be slightly better, and the m optimum will be given by this formula. If you differentiate this with respect to m, right? If you differentiate it with respect to m, and assuming m to be variable and equate it to 0, yeah, okay. See, I have this RC delay. So every time, okay, if you compute the total delay, like we saw in the case of an inverter delay, when resistors where one transistor were cascade one over the other, the same derivation holds good here. Right? For this node to get charged, it will be R equivalent, right, into C, and this will be 2R equivalent into C. Okay, this will be 3R equivalent into C. So these delays will keep getting added up. Okay, so if I write the equation, it will be CR equivalent, okay, into 1 plus 2 plus 3 plus 4, like that. It will keep going on, right? So this is 1 plus 2, because we are assuming this has to get charged first, and once this gets charged, okay, we are taking it as piecemeal and adding all the delays. So this will become so R, this is K, and this has from 0 to n. So there are n number of stages. So this is just a summation of 0 to n, right? Where K, if you do that, you get n into n plus 1 by 2. So this is the total delay. But in case you have in case you have buffers in between after m pass transistors, okay, in that case this equation gets modified here. So instead of n, now it becomes m, right, instead of n, because this plus there will be how many buffers will be there? Total stages is n, and total m, and after every m we are putting one buffer, so it will n divided by m minus 1, because okay, we don't have a buffer in the beginning, so you will have n divided by n minus 1 t buffer, right? So yeah, you can do that at a different interval also. It's not an issue. So you just have to see, like there could be when you implement a path, there could be different in one path there could be 5 PMOS and pass transistors. In one path there could be only 2 paths, right? This we are just speaking of an case where only single path, right? There could be different paths available. Some could be critical paths, some may not be critical paths. So you might want to put some buffers in the critical path. So all those issues will be there. Okay, so now we talk about this equation, and then if we assume m to be a variable and differentiate it and equate it to 0, so you will get m optimum. You will get this equation. Sir, in the transmission gates also output at VDD is not possible. No. If you are using transmission gate, it will be output will be VDD. If you are using transmission gate, output will be VDD. Okay, that is for extra. You have an extra transistor there. Okay, so no, in that case also, if you yeah, in that case you but I think still the buffers will. Okay, you're saying we are using transistors out here. In case we are not instead of this, if you are going to I think still it will improve the delay conditions if you have buffers, right? Because you can, if I explain it in without mathematics, okay, I can tell you. See, generally this inverter will get triggered at an VTM itself, right? So the moment this has reached around a half VTM gross, this will get triggered. So some delay it would cut through. Is it okay if I think it that way, right? This need not go till VDD or till 0. The moment it is slightly below the threshold voltage of this inverter, this will give a full swing out here, right? So each of these buffers, they will do that, right? Because the moment it has reached slightly below the threshold voltage, below the or above the threshold voltage of the inverter, you will find full swings available here. So that will fast up this operation of this chain. Yeah, correct. That's what the propagation delay can be reduced by inserting these buffers, because they will start the full swing. For the input need not swing from VDD to 0. The moment it reaches the halfway through, these inverters will start driving the further stages. So that way it will bring the overall delays. Okay. Is it okay? Shall we move forward? Yeah, in each stage also you can reduce the delay by increasing the width of these transistors. That also can be done. Okay. Now let's try and design a full adder. Okay, how is it a full adder? So this is a sum, right? So if I have to, this is sum and this is sum bar outputs. Okay, so both the outputs I am taking. So for this sum bar at this node, I require sum, right? Okay, now what is the expression for sum? So how to go about designing this transistor? Okay, now these two transistors are just to restore the level. So don't worry about this. Okay, so instead of taking it from here, since this output is available here, I am taking. So these two transistors are just to restore the level. Here I have sum out here. Now what is sum? A bar B. See, this is the expression for sum, right? So at least there is either there is only 1 or 3 ones. Okay, that is the condition. Now I take C in is equal to 0. Okay, now if I put in this expression C in is equal to 0, so these two terms vanish and I have A B bar and plus B A bar. Okay, this is the expression which I get. Now in this expression, so I put C and C bar here, two transistors out here. So C is equal to 0. So I am talking about this C bar path now. In this path again A can be 0 or A equal to 1. If A is equal to 0, sum will be B. If A is equal to 1, sum will be B bar. So now I put A is equal to 0, right? Then it is for A equal to 1, it is B bar, and A is equal to 0, so that's why I am giving A bar here, it is B here. So you understood how this path has been designed? Is it okay with all of you? Right? And similarly, I take C in is equal to 1, right? If I take it C in is equal to 1, then the sum expression reduces to this. Right, and then I take A is equal to 0, what is the value of sum? A is equal to 1, what is the value of the sum? So now this is C is equal to 1, this is the path, right? And again I have two conditions, A is equal to 1 and A equal to 0. Okay, A equal to 0 represents this switch will be switched on, so A bar. So that is what A bar, sum B bar, so I have put B bar here. And A is equal to 1, it is B, so I put here B. So this is how I designed this circuit. Okay, so now I am getting sum here. I am putting an inverter and taking sum bar out here, right? I am generating sum bar here and I am putting an inverter and taking it sum here, right? So this is sum and sum bar here. Okay, this is just to cater for the right for the fan out requirements, whereas these two transistors are for restoring the levels at these two nodes. Is this clear to all of you? Yeah, is it okay? Shall we move forward? Yeah, okay. If you see here, this is a transmission gate, and yeah, you can try it out. Okay, so you'll learn few things by doing that. If you don't get the results, you will know, okay, what is the problem with the sizing of the transistors and things like that, and then you'll get to know the in-depth fundamentals in that case during simulation. Okay, this is how we can implement a transmission gate at XOR. Now if you see here, if A is equal to 0, right, this transistor will be switched on, right, and if B is 1, then this will be 1 out here, right. If B is equal to 0 and A is equal to 1, then again you will find this, and this is on and A is equal to 1, this will become a 1 here, right. So for all the 4 conditions, you will find that this is working as a transmission gate XOR, right. If A is equal to 0, B is equal to 1, then from B this node will get charged to 1, right. If this will be similarly, if A is equal to 1, right, this will be switched on, right, and if B is equal to 1, A is equal to 1, this is switched on, this is switched on, okay, and if B is equal to 1, then this will be 0 here, then this will be 0. If B is equal to 0, then this will be charged to 1. So you will find for all 4 possible combinations, this will work like an transmission gate and XOR. Okay, so you see this is a basic XOR building block. Okay, this has been used to make several other functions also. So you have to understand how an XOR gate. It is A is given here, B bar is given here. Again you have B bar B and A is given here, and the output is taken from this node. Okay, so this becomes the basic transmission gate XOR. Okay, now this has been used for adders also. Now if you see here, we learnt about adders, right, where you have A bar is generated, C bar is generated, and then for adders you have that propagation, right. What is propagation in an adder? So whenever A XOR B is propagation, right, if that means if either A or B, if only one of them is 1 here, then you have the propagation signal high. That means the carry will be carry in will be propagated towards the carry, right. So is that okay? Have we learnt about it, or I have covered that? I don't remember that. Have we talked about propagation and generation of an adder? Anybody? No? No? Okay. Okay. I think it's in the next lecture. Okay. So see, how do I show that? Okay. See, you can for an adder, you have an let's keep it for the next class. Basic thing I'll just tell the very basic, right. What is an let me otherwise show that, otherwise there will be confusion always. Yeah, okay. This is a propagation and a generate for an adder. Okay, so we'll talk in detail about this in the next class, but I'll just give you a little bit hint so that we understand the pass transistor logic. Okay, what is generate means, if I have A, B and C, if A is high, B is high, straight away the generate signal will go high. That means the carry is to be generated, okay, immediately. Okay, what about propagate? It is an XOR of AB. Okay, if it is of XOR of AB, it means that if the propagate signal is high, that means if the carry in is high, then the carry is will be generated. If carry signal is 0, then the carry will be 0. So now once the propagate signal is high, the carry depends on the input. If the generate signal is high, that means straight away carry is generated. Is this much clear? Okay, it is just a simple way of writing generate and propagation. Propagation is XOR of A and B. Okay, it means that one of them is 1. So the carry will be generated depending on the input carry. If the carry is 0, then it will be carry. If carry is 1, then this will be the carry will be carry in is 1, carry out will be 1. If carry in is 0, carry out will be 0. If the propagation signal is high. If the generate signal is high, then you don't have to worry about the carry in, the carry out will be high. Okay, so that is how it is not symmetric. What is not symmetric? Okay, I couldn't see. It means it is A, B, XOR. Okay, generate will be straight away generated in case A and B are high. Okay, propagates. Now using generate and propagate and carry, we generate the carry out here. Okay, so this is what propagate means. Okay, we'll see this in the next class in details on various adder architectures. Okay, let me come back to here. Okay, now if you see here, this is actually a propagate signal is nothing but A XOR B. Okay, that means this is the propagate signal. This is XOR gate, right? So this is also an XOR gate. Only thing is it is the complementary generated here. So the signals have been swapped here. So this is the XOR structure which we saw here. The same. So A XOR B. If you just understand this much for the time being. Okay, can you explain XOR gate? Okay. Let's first try and understand what an XOR gate is. What is XOR? If either A or B is 1, then the output should be 1. So the output is taken from here, right? If A is 0, this PMOS will be switched on, right? If this is switched on, if B is 1, then this output will be charged to 1. So A 0, B 1, this output will be charged to 1, correct? So now A is 0, right, and B is 0. Then this there will not be, this will be 0, right? So that's how XOR works, right? Similarly for other conditions also, if A is 1, right, and B is 0, then B bar will be 1. This will be charged to 1. If A is 1 and B bar is and B is also 1, then this will be 0 out here, right? So this will be so this works like an XOR gate. Is it okay? So see, for all the 4 conditions, this node needs to be charged either to 1 or even this is working, right? Now suppose A is 0, right, and B is equal to right, for other, like let's take A is equal to 0 out here, right, and B is equal to 0. So if you have just this part, okay, if you have just these 2 transistors, then all the 4 conditions, you will have a floating condition also out here. If you can just check the various conditions. So if A is equal to 0 out here, okay, if suppose this is 1 earlier, okay, now that needs to be that needs to be discharged. So it will ensure this is also required to ensure that, okay, at any for all the 4 different combinations, F is either connected to 0 or 1. Okay, so it is, so all these 1, 2, 3, 4 transistors will be required to cater for. Okay, what best we can to do is you make a truth table and just draw the paths, okay, from F to VDD or ground. Okay, so you will find that in all the 4 combinations, there will be one path from F to ground. F to ground or F to VDD, okay, either through this or through that. So you can just do that small exercise for yourself and see that, then you will realize that even this is required for sure. Okay, without that there could be a condition of F floating. So this is generating XOR. Okay, once this is generating XOR, so this P is nothing but A XOR P. Okay, A XOR B. Okay, now you are giving that out here, right, and then you are giving C in as an input. So whenever propagation is high, if carry in is 1, so it will generate the carry, and if the propagation is 0, then it will generate the then if propagation is 0, then then carry will be 0 in that case, in any case. Okay, so this particular two XOR gates have been used to generate the sum and carry. Okay, this part time being we leave it like this. In the next class we will speak about propagation and generate in detail. So this we can revisit this aspect subsequently again, once again, once we learn about the higher adders. Okay, we have just learnt about CMOS adders, and that is 28 transistor adders, and we have not learnt about the carry look ahead adders, and that's why this may not be very clear at this particular stage, but after the next class we'll revisit this circuit. Okay, so this is another way of using pass transistor logic, another application of pass transistor logic for better adder architectures. Okay, so this is a better adder architecture than this. Okay, so these are fast adders. Okay, they are carry look ahead adders, or we'll see about the application of these in the next class. Okay, so before we wind off, let me show you some simulations also. Right, so this is the pass transistor based on a full adder, which we just discussed. So if I run the simulation, so I can plot A, B, C, and let me just plot sum. So similarly I can plot carry also, no problem. A, B, C. So I get this sum, right? 0, 0, 0, 1, single 1 it is 1, single 1 it is 1 out here, and 2 ones it is gone to 0. Again here there is a single 1. Here there are 2 ones here, again here there are 2 ones, and finally you have 3 ones. The sum is going high. So this is out. Now if you see here, I have this keeper transistors, right, to restore the level. So if I just remove that, what happens? Okay, if I remove these things, right, and so I'm still getting no issues here, because I have used an inverter here. But if I plot these signals, right, you will find, okay, this is not going up to full VDD. You saw this signal. This is not going up to full VDD. It is just going. See, this is not going up to full VDD. Similarly, this particular signal is not going. So if you remove these pass transistors, the voltage available at here and at this node and this node will not be full VDD. So that could result in this PMOS transmitting, and when it is supposed to be switched off also, there could be, if the VTH for different technology, you have to be careful with whatever voltage is available. It should not so happen that this transistor is transmitting when it is supposed to be switched off. Okay, so it is always safe to use an this transistor out here. Now if you see the size of this transistor which I have used here, okay, I have used length as 1800 nanometer, right? 180 nanometer is, right, minimum width is 400, right? So I can't go reduce the width below 400, but what I have done is I have increased the length so as to make it weak, right? So I have increased the length to 180 nanometer. Okay, so the sizing of these two transistors, if you see here also 180 nanometer, so I have increased the size. Okay, whereas these transistors I have used slightly larger, so that will So see, this size is not real. This is not again a ratioed logic. Only thing is, if you use large transistors, then the speed will be faster. Okay, so it is not going to. No, there is no actually a rule. It depends on right. It is a direct. The penalty will be area. Right, that is the issue. Otherwise, if you use if you use larger width, you will get a faster response. The penalty will obviously be area, and the signals which is driving these nodes also, you will have a greater capacitance there. So there could be some. Okay, what is the definition of ratioed is whether the output VOH and VOL is it a function of the transistor width. Okay, now here in the CMOS, right, even if you increase the size of the NMOS and PMOS, if you decrease, the output will be VDD or ground, right? It won't change. It will be VDD or ground. So it is not depending on the width of the transistor. Only thing is, now the delays will change, right? Whereas if you remember when we learnt about the resistor NMOS topology or the depletion, the output voltage VOL and VOH are not a function of the width of the transistor. So we say it is a ratioed. Is it okay? Yeah, you can say all rail to rail. No, I think all your EC1 components are over now. Okay, thanks a lot.